Alrighty, let's talk real quick before we jump into warm-up. I think most of you, if you haven't figured it out, I think that you probably found yesterday's homework to be not incredibly difficult. This entire unit is very, very calculator-driven. That's why we save it till the end. That's why we only do 4 days on it. It's a very calculator-driven unit. Same thing is going to happen today, except today you're going to learn a formula and how it applies in real life. Remember, when you come back off the weekend, we have Monday, we have Tuesday, and then everything's about the EOC. To put it in perspective, 1 week from today will be your last review day for the EOC. 1 week from today will be the last day we actually review for the EOC. Then you'll come back off the weekend next time. Monday we'll have a strategy day. Tuesday you'll be here for the test. Remember all the kind of things you need to remember when you take a STAR test. Y'all will be the only group in the building taking the STAR test that particular day. We'll have room assignments and everything for you sometime next week. But it's the same thing. You'll come in, it's a 4-hour test. Come in, bring your snacks, get some rest the night before, all that fun stuff. Yes, sir?
So it's for the only ones like taking the test, once everyone's finished, we get out of testing mode?
Once every algebra student's finished, y'all are out of testing mode. Yeah. No, they're not. But thank you. Basically, what we've done is we've basically taken this entire side, and it's nothing but algebra EOC testing. Oh my gosh, really? Because we have degrees and you don't?
Oh.
Hey, Josh. Hey, Josh. If you're looking for an explanation as to why your grade is starting to dip, this could be it. Okay. So, and then you're basically done with algebra. Okay? So, let's kind of go through the warm-up, and then we'll get into the way that word problems work with exponential growth and decay, and I think you'll find today to be pretty straightforward and easy as well. Number 1 says, given y equals 3 to the x power, evaluate y when x equals 3. When you get one of these problems, what are you simply doing? You're simply plugging it in. You're simply substituting values in. This value goes in for x, so it's basically 3 to the third, 3 to the third. Spencer, you want to go upstairs? I'm sorry? Had nothing to do with the conversation. I think you know that. Got it? Fantastic. 3 to the third power is 27. Given y equals 3 to the x, evaluate y when x equals negative 2. And by the way, you really shouldn't need a calculator for most of this stuff. If you remember negative exponents, what happens when we have a negative exponent? You're going to flip it. This is the same as 1 over 3 to the second, which is 1/9. And finally, would the graph of y equals 0.5 to the x power show exponential growth or exponential decay? Someone give me an answer and tell me why. Danny. Why? Because the base is less than 1. Excellent. Anytime the base is less than 1, it shows decay. Would the graph of y equals 1.5 to the x show exponential growth or decay? Obviously growth, because the base is greater than 1. The equation y equals a to the x will be an exponential function when a equals y. Who said y2? Did anybody just put it in as y equals 1 to the x power into y equals and hit the graph button? Yeah, that's all you had to do. And it was a straight line. It's a straight line. Why is it a straight line? Because 1 to any power is 1, no matter what. Okay? 2 is the only acceptable choice. It's the only one that gives you that typical exponential shape. An exponential function will either look like this or will look like this. Okay? It's the only shape an exponential function will ever be. Now, if you think about it, I will tell you this. When you get into exponential transformations, which you can shift an exponential function up or down. You can shift it right or left. And you can vertically stretch it. You could horizontally stretch it. Okay? You can still do all the same transformations, but the basic function looks like that. Which ordered pairs represent the y-intercept for the function y equals 2 to the x? 0, 1. Did everyone just put that in the calculator? Yeah. Did anyone yesterday determine how you find the y-intercept, Muhammad?
It's multiplied by 1.
When you look at an exponential function, it's usually y equals, it could be y equals something times something to the whatever power. This is always your y-intercept. If you didn't see that, if you will in your calculators type in y equals 3 times 4 to the x power, I will guarantee you the y-intercept is 3. I will guarantee you the y-intercept is 3. Okay? And in this case, since you don't have a number in front of the exponent in the base, it has to be 1. The graph of y equals 2 to the x lies in which quadrants? 1 and 2. Did anybody forget the quadrant trick? Okay, quadrant trick. Here's your quadrant. Yes, that's right, Danny. C, it is the letter C. If you do the capital letter C, it starts in 1, then it goes to 2, then it goes to 3, then it goes to 4. You'll do it in the order in which it's done. Coordinate grid, capital C. Okay? And finally, the graph of 2 to the x contains which of these points?
C.
Why? Because the calculator said so.
That's why.
Because it's the y-intercept, yeah. And which graph below depicts 3 to the x plus 2? Now, before you say go, what do you think 3 to the x power looks like? It looks like this, right? It's exponential growth. And it's approaching the 0, the axis, right? The x-axis. What kind of a shift is this? Vertical shift up 2. Therefore, it went up 2. Transformations are basically the same as they did when we did transformations, quadratic transformations, linear transformations. Does not matter. Okay, it's all the exact same. Any questions on that? All right, good. Let's get into the exponential formula. Exponential growth in Decay can best be defined as when an amount increases or decreases by a fixed percent. We gave that analogy yesterday where we talked about me walking to the wall. And I would walk halfway to the wall, then halfway to the wall, then halfway to the wall, then halfway to the wall. And theoretically, I never get to the wall, which is why you get that particular shape when you have an exponential function. It gets closer and closer and closer to a number, but it never actually gets there. By the way, what if I changed my strategy? What if I decided to walk 99% of the way to the wall and then stop? Still wouldn't get to the wall. Because anything that has to do with percent does that. Anything that has to do with percent, you never actually get there. Because you're always leaving a little bit there as you get nearer and nearer. There are formulas for exponential growth and decay, and they look like this. And if you'll notice, the only differences between the two formulas, the adding and subtracting. The adding and subtracting. Very important formulas to get in your head because you don't get them on the formula chart for algebra. But they will absolutely be on your EOC. Because I don't make the rules. Why are you asking me? Go to Austin, ask the governor. But for right now, what I do know, it used to be on the formula chart, and then 2 years ago when they changed it, or 3 years ago when they changed it, they took it off the formula chart. And I think primarily because if you look at the formula really closely, it's exactly like the compound interest formula. It's basically the compound interest formula. Starting point times the rate to the time power. We'll get to it later. You'll either recognize it or you won't. It doesn't matter that you have to memorize it. Okay? The only differences are the plus and the minus. So let's talk about what each thing represents. The A value is the amount that you start with. Now that could be money, that could be people, that could be germs, that could be whatever. Potatoes. It can be land. It can be whatever amount that you begin with in the scenario is your A value. The R is your rate. The rate is often found in word problems as a percent. It is always converted into a decimal before you use it. You must convert percents to decimals. And it's like a rate of change. So if it says so-and-so grew 17% each year, then your rate is 0.17. Now, there are a couple of things that you'll see with regard to the rate that aren't crazy obvious. Sometimes you see the word half. Then sometimes you'll see the word double, and sometimes you'll see the word triple. What do you think the rate is for half? 50%, which is 0.5. 50%, which is 0.5. What do you think the rate is for double? Wrong. Watch. Listen. Just listen. If I'm here and I double, how many of me are there now? By how much did I change? 1. The rate is a rate of change, and every kid in the world has to pause when you see double or triple. Because if I double, the rate of change is actually 100%. If you double, the rate of change is actually 100%. If I triple, it's 200%. Because it's by how much I changed. So be very careful about the words double and triple. Now, how would I convert 100% into a decimal? What is 100% as a decimal? It's 1. And if you're not sure how to convert a percent to a decimal, you simply divide it by 100. Whatever the percent is, divide it by 100, bam, it's done. Okay? And finally, the x is the number of time intervals that have passed. And it's very important that you understand it as time intervals, and we'll have an example in the notes in just a second that kind of explains what that looks like. Because that's usually, if a kid's going to mess up, it's either going to be on the time intervals or it's going to be on the double, triple thing. Good to go? So let's see. A bank account B for an account starting with S dollars earning an annual interest rate R and left unattended or untouched for N years can be calculated as. That was a big freaking long sentence that only served to give you the formula. They just changed the variables, but it's basically the same formula. This is still the starting amount, this is still the rate, and this is still the number of time intervals. So now we just need to identify what each variable is, and we plug it into the equation. Find a bank account balance to the nearest dollar, if the account starts with $100. Therefore, that's our starting point, $100. Has an annual rate of 4%, so 0.04 is our rate. And the money is left in the account for 12 years. For 12 years, that's our n, or our exponent. So we simply start with the formula, and we plug everything in. And once we plug everything in, by the way, how did we know that this was the growth? How did we know to use the plus sign? Okay. How else might you know?
It says it has annual rate.
The word earning.
Yeah.
You will find little hint words that tell you whether it's decay or whether it's growth. If it's earning, it's getting bigger.
So like withdrawal.
That's exactly right. Yeah. Once we plug it in, it becomes straight calculator. You type in 100, go ahead, Spencer. 100 parentheses 1 plus 0.04, close parentheses, caret 12, you get $160, and that's how much is now in the account. That is now how much is in this account. Now, I can't imagine they would ask it, but if they were to ask you how much interest they earned, what would that number be? It would be $60 because they started with 100, and now they have 160. So make sure you know what they're asking you for.
And interest per year would be $5, right? Because they look in this.
No, it's exponential growth. It did not grow $5 every year. It grew less than $5 the first year and worked its way up. Okay?
So if like we subtract what we started with before,
Yeah. Now here's a question. What if instead of an annual interest rate, it was a semi-annual interest rate? What? It's twice a year. What would have changed?
it would be 20.
It would be 24. Because if the interest rate happens semi-annually, which is twice a year, then in 12 years, it would have happened 24 times, which is the number of time intervals. That's where you have to be careful. That's where you have to be careful. In this case, it was annual, so it didn't matter, but I just wanted to give you an idea of what it looks like. Let's try this one. Each year, the local country club sponsors a tennis tournament. Play starts with 128 participants. That's where we begin. During each round, half of the players are eliminated. What do we just get?
Decay.
We just get the decay rate because we got decay, so we know it's minus in the parentheses, and we know the rate because it said half, so it's 0.50. How many players remain after 5 rounds? That's our x value. So we take our formula and we plug it in. 128 times 1 minus 0.5 to the 5th power. And when we plug it in, we find that 4 players remain after 5 rounds. Pretty straightforward. All right, let's do one more and then you'll get into your classwork homework stuff. This one gets kind of interesting, so I would kind of pay attention to this one. Your baby brother has an ear infection. The doctor said there are probably 50 million bacteria in his left ear. 50 million bacteria in his left ear. That gives you a starting point of 50 million. The penicillin the doctor prescribed will kill 7% of the bacteria every 6 hours. This tells you it is decay. This tells you the R value is 0.07, and it tells you the time interval is every 6 hours. So let's begin to construct the equation. In one day, we will start with our starting point, which is 50 million, times 1 minus the rate of 0.07. And in one day, how many 6-hour intervals are there? There are 4. That is your exponent. Because your exponent is how many time intervals there are in the scenario. Yes, ma'am? How did I get what? It says it happens every 6 hours. How many 6-hour segments are there in one day? There are 4. Yeah. So as easy as it is, because it's calculator driven, if you don't set it up right, calculator's just going to do what you tell it to do. So, wait, Danny, read it off to me, please.
374.
Wait, say it in like, correct. Say it properly. 37 million.
402,600.
Is that exact? 0.5. That is the answer that needs to be right. If you get a number like that, I want to see comma separators. Okay? It is. So now every 3 hours, let's set it up. It should be a very similar equation. We still have the same starting point, 50 million. We still have a decay rate of 1 minus 0.07. And it is to the 1/2 or 0.5 power, because there is half a 6-hour period interval in 3 hours. And once we punch that in, hold 48 million.
218,253.8.
218,253.
And that is your answer.
Why did it kill more in 3 hours than 1 day?
That's how much left.
It didn't. That's how much is remaining.
Oh,
Now, by the way, a couple of quick things just to talk about. Let's go back to the original equations. How could we tell that an equation was exponential growth? Where did we always look? Yesterday, at the base. And the base had to be? Had to be greater than 1. That's why it's 1 plus the rate. Anything that's above 1 is a rate in the parentheses. Any base that is greater than 1 is growth. And we knew it was decay if it was less than 1. That's why it's 1 minus the rate on decay. One other quick thing. If you will type in to your calculators, let's go to this. I want you to type this equation in, but I want you to type it in without the time interval. So I want you to type it in as 50 million. Go to y equals, type it in as 50 million times 1 minus 0.07 to the x power. Type it into y equals as 50 million times 1 minus 0.07, but this time instead of a time power, do it to the x power, and then I want you to go to the table. No, it is not. Now, shh, everyone listen up. Did you get yours? Did you get yours? Here's what you've got. At 1, you should see 4.65 E7. Now, I want to explain this. Do you remember when you first learned about scientific and standard notation, and we said that we use scientific notation when the numbers got too big? It was a more brief way of writing large numbers. This number is essentially 4.65 times 10 to the 7th power. This is scientific notation. And if you'll remember back when you had to do that, you would move the decimal 7 times to the right.
So the E is like
It means exponent. So when you see that in your table, understand that this would be the answer choice you would likely see on a test. That would likely be the answer choice you would see on a test that you would have to choose that is the same as this. Yes, ma'am.
would the 7 would ever be like behind the E, would it ever be a negative number?
Yes. If it gets smaller. By the way, that's also, if you remember exponential decay, it does this, and it gets closer and closer and closer to 0, right? If you go to the table of this function, probably around x equals 20, it will simply give you 0 as a y value. It's not 0 as a y value. It just gets so very small that the calculator basically has to round it to 0. So, understand, what I need you to understand, this was a question that was on the EOC a couple years ago. They gave them an exponential decay problem, and they said, at an x value of whatever, which of the following represents the y value? And there were tons of kids who just went to the calculator and saw this and said, oh, it's 0, and selected 0. It's wrong. It never reaches 0. It never reaches 0. The calculator just rounds it to 0. So be very cautious about that. Make sure you understand the way that it goes. You have classwork and homework today. It should not take you very long on either one. I'll put the answer keys out, and then you are done for the day. Make sure you turn in your homework from last night.